The Nash bargaining solution is that which maximizes the product of utilities for all the parties. So we are maximizing U1 times U2 times UI, which is equivalent to maximizing the sum of the logarithms for all the parties. Now, what is interesting is that the Nash bargaining solution, which maximizes the product of utilities, is the only bargaining solution which satisfies all of these axioms or properties that we've just looked at. Namely, it is Pareto-optimal, it is symmetrical, it is invariant to linear transformations of utility functions of the party, both independence of utility origin and utility units, and it is also it also satisfies the independence of irrelevant alternatives. And there's a proof of this result in the textbook, in our textbook, Mascolel, Winston, and Green, and I'll do a short tutorial on that proof. Now the Nash solution, Nash bargaining solution, not to be confused, by the way, with the Nash equilibrium. The Nash bargaining solution satisfies a simple geometric property, which is as follows. If you consider the utility possibility set U, you are trying to find a point which is going to be on the boundary, right? So, because of Pareto efficiency. The shape of the indifference curves of the Nash product, which is the product of the utilities of the party, is a hyperbole. So the indifference curves are hyperboles. So this is U1, U2 equals to some constant. Now at the tangency point, this here is the Nash bargaining solution. This is the tangency here. Now a very interesting property is that the Nash bargaining solution is actually the midpoint of the tendency line. So I need to complete my drawing here to show you. If I go back up, this is not really drawn to scale, but this point here is the actual midpoint of the tendency line. The Nash equilibrium point also happens to be on the XY line, the 45-degree line. Maybe switch color. So these are the geometric interpretations of the Nash bargaining solution. Now what I want to do is derive the Nash first order condition for you, for the Nash bargaining solution. I'm going to assume that X is simply the share of the surplus, which is being allocated to person 1. Person 1's utility is V of X. Person 2's utility is capital V, defined over 1 minus X, because person 2 gets whatever is not being allocated to person 1. So here in this framework, you'll note that X is the share going to person 1. If X is equal to 0.5, the parties will split the surplus 50-50. So the Nash product, the Nash product is simply V of X times capital V1 defined over 1 minus X. If I take the first order condition, I get V prime times V plus V of X times V prime times 1 minus X times minus 1. y minus 1 because I simply apply the chain rule here. I take the derivative of what's inside v prime with respect to x, and that happens to be minus 1. And this here is equal to 0. Kind of ran out of space. Equal to 0, so that simplifies to the ratio v prime divided by v is equal to the ratio of capital V prime divided by capital V. So the first order condition here simply says that the ratios of the marginal utility gain defined as a percentage or as a proportion of the total utility experienced from the allocation of a share of the surplus must be equalized for both parties. Now, as it turns out, the interpretation of this is that the person with the most concave utility function actually gets less. So the Nash equilibrium rewards the less risk-averse person, and the person who is most risk-averse, who has the most concave utility function, is actually gets quote-unquote penalized or gets a smaller share of the surplus. If the parties have the same utility functions, the parties will split the surplus equally. But if they don't, then the person with the lowest marginal utility actually gets, the person with the marginal utility which diminishes most rapidly actually gets a lower share.